That about in a rather circuitous way. One of my favorite authors is Simon Winchester, who wrote a book called Krakatoa. And then I started reading every book that he wrote and every book that he recommended. And one of them was called Cascadia's Fault, which I read a few weeks before I was headed up to a conference in Seattle. And I changed my hotel because of it. And yeah, exactly. I didn't want to be on the wrong side of Highway 5.
Education saves lives.
And in the book, Vasily's work was mentioned, and I was stunned by quite a few things in tsunami modeling, and where it's gone, and the real challenge that they have to put out these alerts, because when the Cascadia earthquake happens next, it is going to be amazingly devastating, and this is something that we need to even worry about down here in California. So, that's it.
Thanks very much for the introduction, and thank you for inviting to the excellent talks. I was really impressed, with the breadth and the depth of the things. So what they were presented. Guess I'll shift a little bit gears here. We back to Earth first of all, mostly, just to introduce. Well, to introduce the problem, what do we have to deal with to do the tsunami forecast and warning? And the reason we do the forecast, I'm involved in the forecast and warning. I work for the NOAA, National Oceanic Atmospheric Administration. That's the science agency, but they have operational component, actually a big component. It's the biggest component of NOAA, and part of it is weather, of course, forecast, weather service. But the weather service also do tsunami warning. So tsunami warning is done by this operational part of NOAA, and it's in two warning centers. Two warning centers do operational forecast and warning. One is in Alaska, and one is in Hawaii, which is also International Tsunami Warning Center. So they provide 24/7 tsunami warning capabilities. I work for the research part of NOAA, which is a smaller part of NOAA. Obviously, the research usually is a small part, and we provide science support for this warning operation. So we're developing tools mostly for the forecast. So that's what my connection with tsunami is, and I'm still consider myself a scientist, although it's NOAA is an agency, but it's a science agency. It's a very mission-oriented agency. So what I want to do in this talk is just introduce the problem first of all. Why do we care about tsunamis? How do we do this? Why do we need tsunami warning? How do we do tsunami warning, and what are the challenges that we still face? So that's sort of the bulk, the outline of the talk. So what's the problem? How big is the problem? You probably know about tsunamis from just one, maybe two, maybe three events that you hear in the headlines, but they're actually happening all the time. It's just and now with the internet they're becoming more known, but it's since you may have heard about the Indian Ocean tsunami, the Japan tsunami. But since the Indian Ocean tsunami, which happened in 2004, there were 50 tsunamis happened somewhere over the world, and most of the impact, of course, was from these two tsunamis. But in the 15 years, almost 15 years, that has gone since the 2004, which was really watershed event in terms of the tsunami science and tsunami warning and forecast. There was almost 250,000 people died from tsunamis, mostly from these two events. $250 billion in damage. So it's pretty pricey hazard. That's worldwide. And again, most of the people killed actually is in the Indian Ocean from the event. The star is right here. But most damage is actually most monetary damage is from the event in Japan, which is also still, you know, over 16,000 people died there, but nothing compared to the Indian Ocean event. And there haven't been any, you know, major tsunamis in the coast of U.S. actually, but U.S. has spent over $100 million on mitigations of all these events, all those 50 events over the years. So to me, this is the sort of the number that gets my attention, because we $100 million spent for an event that hasn't even happened yet. So that if it's going to happen at the, you know, near the coastline of the U.S., it's going to be a major impact, and that's why we try to minimize, to mitigate the damage and the hazard. Right. Well, actually, that's so. The U.S. actually spent $1 billion for all the events. There was the small event. The event. There were actually events in the U.S. It was there was in 2009 there was tsunami in Samoa, and Samoa is U.S. territory, and there were people killed there. So that's the major U.S. caused impact of tsunamis. Yeah. Right. So the tsunami science it started like back in 1930s in Japan, really, and the focus of that is to forecast tsunami. From the very beginning, it was how can we say something about the potential tsunami that's happening, and the way it was done, you know, in Japan in 1930s, it was just based on on really the power of the earthquakes. So you get some estimate of the earthquake magnitude, and that's a proxy for the tsunami power. Very, very crude estimate, by the way. But from the very beginning, you know, there was from the very beginning of the computational era, you know, the numerical models, the idea was, we can run numerical models ahead of time, and then that can produce the forecast that's much more accurate than just the ballpark numbers that you can get from the earthquakes. And then what was done, it shows the animation, the model animation of, fairly crude actually, model of the 2004 Sumatra tsunami. That's the one that's killed almost, you know, nobody knows exactly when, but over 200,000 people. It was probably the first model that was done in real time. And I say sort of because it was, when this model was complete, the wave was actually hitting the Africa here. It was devastating all over the Indian Ocean. It was about 8 hours into the event, and they was claiming the last victim right there in the south, in South Africa. So it wasn't by any means a real-time forecast. But what happened after that was that the demand for this data, for this very crude model, it was fairly crude, you know, low resolution, with very ballpark estimates of numbers around the world. The demand for this data was huge. The reason was that it was the only measurement-based data that's available especially from ground zero for many hours, days, and weeks, actually. So that's additional interesting value of the forecast. It's not, you know, the forecast doesn't end when it doesn't have to be, you know, producing the numbers before the wave hit the coastlines. It actually extends further out, you know, for all the search and rescue operations. That example showed that the value of the model forecast is amazingly large. And we didn't even know how accurate this model was. This was done, the model was based just on one data point. There was the tide gauge, like the Australian tide gauge about here in Cocos Island, and that was the only data set that was used to constrain the model. Because the model, you know, I'm the model myself, and that's the model that I've done. I know the model can do whatever you want, you know, it's just like whatever you put in, you know, you can get whatever output you want. So constraining it by data, it's the key for the forecast, as far as I can see. And the problem with tsunami is that the forecast time is so short. And again, this event was so huge that even this, you know, after 8 hours, it was still, the wave was propagating, and we were able to predict some before.
Are you also using data of just arrival times in, you know, far off places when people tweet, say a big wave just came?
Not yet. Social media is definitely a huge resource that hasn't been tapped into. And I heard this, yesterday there was a presentation about the traffic flow modeling, where the main data set is now the cell phones that everybody has now, and cell phones has a lot of actually gauges that can be used, but no, that's not done. I'll explain. Sorry, it's probably.
What's
explaining it too
follow
long.
on to that? What's also interesting, I spoke to the people at Google who do emergency response. There's a whole philanthropic part of it, and one of the things they look for is lack of social media to see where areas have been devastated, because nobody's tweeting.
That's right. Yeah, we're definitely entering the era of huge amount of data, and we still don't know how to tap to all of it yet. And again, and that was really the beginning of the idea that the forecast can be done, and it's very useful, and it's not just for saving life of people immediately near the source, but for much a wider use actually. So just to give you a brief example, a brief sort of excursus of the model developing, how has it been developed and into the actual operational forecast that we have right now. In this sort of the state-of-the-art animation of the model that was done in 1975, the shallow water wave equations. That's what we could do, in 1975. In 1999, I've done the animation that looks much better, but it's used the same equations pretty much. It's a high resolution. It looks very realistic too. You can do the much more realistic than in 1975. But basically, it's the same equations, the same model. More resolution, more computer power. We still could not do forecasts in the 90s. It was a huge problem. Part of it was that the computers were still much slower than now, but the other part was actually when we sat down with the community and looked into the problem, there was lack of data. We didn't know how accurate this model was because of the lack of the observation data, and there was no data to constrain the model again. So that's the key. So that's what the community would. And tsunami community is a fairly small community. Before this 2004, which really expanded the field, there was maybe 50 or 100 people that everybody knew each other. It's a sort of the club, the small club of very good people, by the way. So we put together a program to actually get this data that we need, at least to see how accurate these models work. Because the model, if shallow water wave equation is fairly crude simplification of the Navier-Stokes equation. There is a lot of assumptions there, and they seem to fit into the tsunami physics, but how well, we don't know, because unless you measure it with the realistic data, you don't know. And that's what there was a team formed, sort of informal team, that went to this timeline. I just put it in the timeline, and the red dots are the tsunamis that's happened. Every tsunami pretty much was surveyed by the team of scientists to get the actual measurement data. Because unless you go there and actually measure like this with sticks, and then now with the laser range finders now, the data is lost. It's very perishable. In a couple of weeks it's going to be cleaned up. And the only thing that you will have left, unless you have the instrumental tide gauge, which are not very, very prolific, when you look at the map, it looks like there are many of them. But whenever tsunami happens, there is no data there. It's just a Murphy's law. So you have to go there and measure the actual, what we call run-up, the vertical elevation of tsunami at long land, and that's something that or any information you can get. That's the sort of the most sort of quantitative information that you can get out of that. Unless you do that, you get only the eyewitness reports. That's pretty much like saying that there was a wave as high as the sky that came and washed everything out. So it's not very quantitative. You can't use it for models, for comparing with the models. At the same time, there was there was a very concerted effort in NOAA, by the way, to come up with the instrumental, real-time instrumental data for tsunamis. There was this deep ocean detector that was developed over the years. It was a huge engineering effort that sitting in the middle of the ocean and sending data on the satellite and measures specifically tsunamis. Very accurate. It's because it's a separate talk probably to say all the to describe all the engineering problems that will have to be solved. But it's a detector that's sitting on the bottom of the ocean, measuring pressure, sending data to the buoy acoustically because the wire is just too long for the buoy to hold, and then it sends it to satellite. So a fairly complex system just to measure the tsunami data. The reason it's in the bottom is that we want to filter out all the wind waves. We want only very long waves, which are tsunamis, and that can be done if you're sitting on the bottom of the ocean. The pressure will be felt only from these waves, from these big waves, and we can measure this. The detection. This instrument can measure tsunamis about this high, centimeter high, and that's a key. Because the tsunami in the deep ocean is very small, so you need to get a very high resolution that you can measure very small waves to propagate them to the coastline that can be devastating. So these two things sort of came together, and we were about to do the prototype things when this big tsunami in 2004 happened, and that speeds things up very much. There's a lot of things happened there, including the act of Congress that established actually by law that NOAA has to provide forecast using the data and the models, and that was then very intensive effort to develop this forecast. And in 2013, it was actually implemented as a capability. And that's the capability. It's actually a fairly complex system, but that's the simplest we could come up with to do this real-time forecast. Again, the problem there is that it has to be done in a very short amount of time. Short amount of time means that for any tsunamis happening along the Ring of Fire, if we take the Pacific, for example, and we're talking about the seismic generated tsunamis first. It's not all of the tsunamis, but that's about 80% of the problem, 75% of the problem. There are other mechanisms that are much more difficult to do the forecast for, like landslide tsunamis, volcanoes in this Krakatoa, asteroids, by the way. Yeah, I'll mention that a little bit. There's meteo tsunamis from meteorological sources, but they are all this 20% of the problem. That's this 80-20 rule that you have 80% of budget we usually spend to 20% of the problem. So it looks like we've done like 80% of the problem, but now the hard part is left. So the system, again, since the forecast is, you run models ahead of time, that's the forecast, but models have to be constrained by data. So it's based on data, and that's the DART, is Deep Ocean Assessment and Reporting for Tsunamis, these triangles, yellow triangles. That was a huge effort of this during the 5 years to develop and implement and actually deploy this system across the oceans. It's all over the place. And nice thing about it is this international community actually picked up a big part of the problem is third of the array is now supported by international partners, which is fairly unprecedented actually. It's a US technology bought by other countries and being used together now. All the data is streamed in real time for everybody to use. You have to invert this data for the modeling or put this data into the model. So model assimilation is not the trivial part, and mostly because it's such a short time. Well, the short time means that the closest coastline is going to be hit by any tsunami is probably about 20 to 30 minutes. So that's the time constraint that you're working against. And I'll tell a little bit more about it, but the bottom line is, well, some coastlines will have 24 hours. For example, if the tsunami is in Japan, the Chile, or the other way around, Chile will receive the waves almost a day after. And they can be very large waves. The 1960 tsunami killed over 200 people in Japan. And Japan tsunami didn't kill any people there, but there was substantial damage in Chile. But the most severe impact is near the source, and that's 30 minutes, an hour. I'll show you what exactly that is. So that's why the data ingestion should be very fast. And the way to do that, we actually pre-compute, since it's modeling forecast, so it's an inversion problem. The way we did it, we pre-computed pretty much something similar to Green's functions that we can then combine without recomputing all these solutions over and over again. So we can fit the measurement data with observation, the measurement data with models very fast without computing a bunch of simulations. So that's the data ingestion, and then you actually produce the forecast. You take these fairly low resolution models that you use to reproduce the data at deep ocean, and then zoom into the coastline. And when the tsunami approaches the coastline, the scale of the problem changes quite a bit. You know, the length of the wave changes almost the order of magnitude, and the amplitude. That's why the amplitude increased just by the conservation of the momentum and mass. And you have to use much higher resolution models, which you can't use uniformly throughout the ocean. So we zoom in with the nested grids type of approach. So that's the system, and that has to be all work together in, you know, ideally in seconds. We're not there yet, but that's what you have to do.
And then do you run higher resolution models later to help with search and rescue and things like that to hone in on things, or is that?
Yeah, well, this forecast model definitely, we provide data. It's now available to everybody. Although it's a very thorny question too, because say in real time the message should be very actionable and clean. The modeling results usually are not that message. So you have to really distill it into something, the actionable results. So the main goal is to save people's lives, right? So the people can evacuate. If you put a lot of, you know, scientific graphics into the message, that may actually be counterproductive. So the discussion now is how much of the information has to be put, you know, has to be made public. For the search and rescue, that's a no question because there is some time there. But in terms of the actual warning and forecast, how much of the data that we produce should be put into warning? It's not a trivial question, in fact, and there's a lot of social studies done. You know, how exactly these messages should look like, and how much information do you put in there? So here I'll show you a lot of information. But we have a wealth of information, but most of this information is now sitting in the tsunami warning centers for them to make a decision how to produce the message. But so yeah, in general, so that's, you know, you measure tsunami, you ingest the data, you do the data inversion for the models, and then you produce the forecast. The forecast is actually that. It's great to know how the tsunami. So that's actually the measurement of tsunami in deep ocean. You know, that's the buoy, that's the surface buoy. That actually it's just a transmission device, but it transmits this data. The black is actually it's for this Japan Tsunami, the closest buoy for the Japan source. And this is the record. This is almost 2 meter high amplitudes, which is huge. It doesn't sound like much if you go to the ocean, and, you know, 2 meter wave is nothing really, you know, unusual. In the open ocean for tsunami amplitude, this is huge. This is catastrophic tsunami, you know, propagating. And in fact, when we saw that data first, we were teaching the modeling course in Tanzania, in Africa, after the Indian Ocean event, capacity building efforts, and this data was already available online. The estimates of the earthquake was very low. That's another problem. That's why the earthquake is a bad proxy for tsunami impact, because there's a lot of problem with assessing the magnitude first, and then the magnitude of the earthquakes does not necessarily correspond to the power of tsunami. And we saw this 2 meter wave coming up in real time. That was really the epiphany moment. They said that this is a huge tsunami propagating. So that's and usually we have 1 or 2 records for that. So the problem there is that you have very little data to constrain your models. So you have to put a lot of assumptions into the modeling to get something meaningful out of this very little data. You know, 2 points with, well, there's a time series, of course, but there's still, it's very little data to constrain it. to model without any constraints. So you put a lot of constraints, and constraints is really just the historical data sets of the sources that have happened before.
In terms of other observations, I mean, can you do task satellite SAR? Can you say with SAR?
Satellites. Oh, sorry. In fact, let me go back here. I didn't mention it. This is actually the data, the only data for the open ocean data for the Indian Ocean tsunami was from satellite. But there was the first and pretty much the only data set from satellite that we saw a tsunami at.
So that's the track?
That's the track, is the orbit, yeah, is adjacent. There are several satellites actually. The altimetry satellites flew through. The black is the data from the satellites, and you can see how noisy this is. This is the cyclone, for example. So that you have to do a lot of data massaging before you can see actual tsunami signal there. And there was weeks of data analysis that we could then use that and then put the blue is the modeling this model, and it compares pretty well, but that was definitely not a real-time effort. It was research effort, and that's the best example of satellite altimetry. Well, there is a new generation of altimetry satellites that are flying now, which I think have a better resolution, but the noise is not going to go away. There's a lot of noise in this data. And then it was just fortuitous that the satellite flew over this area about 2 hours into the event. So they could catch tsunami while the amplitude was still fairly large. It was about 60 centimeters, by the way, here. In Japan, it was about the same time after the source. It was, actually, no, it was closer to the source. It was 2 meters almost. So, but at that time there was no satellite at that particular moment. So then, Japan Tsunami actually, there were some papers that looked at the satellite data, but they were not as clear as that. So it's a difficult problem to see from satellite because it's difficult data to see from satellite.
The design point for those satellite-based altimetry that's meteorological.
Yes. Exactly. And well, to put up a satellite specifically for tsunami purpose, that hasn't been very popular yet. It's an expensive proposition. The whole tsunami program is about 25 million per year, so it's not a big budget item there. So if we can use some satellite platforms to get this data, it would be great. And there are some ideas. For example, GPS has interesting capability. They were able to see the disturbance in ionosphere that the tsunami creates could actually be seen on the GPS signal, and that there have been some data, some papers that are looking at that. But it's mostly this data, for what I've seen so far, was mostly quantitative. They could actually see propagating tsunamis in terms of the amplitudes and quantitative numbers. It was very uncertain. So let me just fast forward again a little bit. So that's so we do all this, the modeling of the open ocean propagation, and it's great to know that it compares well. But the actual forecast is the impact on the coastline. Unless you get this, I mean, this is just for us, for scientists, to look at the beautiful, comparison of the lines, and just to show you what exactly we want to model. I'll just show this. This is a fantastic images. In Japan. It's a Japan 2011 tsunami. They call it 311, the March 11 of 2011. They streamed the event real time because they had this. In Japan, the broadcast companies actually had agreement that they were having helicopters ready in case of things or something like that. So they broadcasted it live, and you could see that's the inundation, the tsunami inundation that we have to model with our forecasts. So for example, this is a supercritical flow. That's how it looks like in tsunamis. Very difficult to model, by the way. It doesn't look like much in here, but you can see that the flow is actually it's far from nice and clean hydrodynamic flow. It's definitely it's much more complex because of all the debris, and you see the color of the. I don't know if you saw the color of the water is black. It's completely black. It's not. And it came from the ocean. Just to give you perspective, a little bit of the scale of the event. You see the fires. Interestingly, it's very often associated with tsunamis because when it picks up debris, if there's some flammables there and some electricity, then the fire starts and it carries it through to other locations. So fires are often accompanying tsunamis, and the power, of course, you can see that shows that nothing can withstand this huge tsunami, and it's definitely nothing like this nice curly wave that you see often in the pictures of tsunamis. It's really something really dirty and powerful that bulldozes everything away in front of it. So that's what we want to model. And Japan was definitely a wake-up call. Japan is the most vulnerable, country in terms of the tsunami hazard, and it's definitely the most prepared. And it's still there is a lot of problems that 16,000 people died there, and it's not the most populated coastline that's this tsunami hit. It was a huge tsunami, definitely. The forecast was, it's forecasted in real time. The problem is that the forecast is much underestimated there, again, because of the initial underestimate of the earthquake. The assessment of the amplitudes were very underestimated. That probably caused some additional casualties there because some people did not evacuate those that should have been evacuated. It's interesting reaction from the operational warning community is that the GMA, the Japan Meteorological Agency, that's responsible for the warning, they say we are not going to be issuing amplitude forecast anymore because it's misleading. So it's typical bureaucratic solution to the problem. We're just not gonna do that so that we don't get blamed for the liability. And that's, it sounds cynical, but it's actually, the wrong forecast kills people too. So unless you're absolutely sure that you can do it accurately, it may become counterproductive to do that. So it's a complex problem because it's so much compressed in time.
Is the buoys that you talked about, of course, they're only valuable due to their relative distance to the epicenter versus the coastline's distance to the epicenter. Are there enough to help Japan?
Well, okay, I'll hold this question a little bit. It's difficult. I'll show you some illustrations of that. No, the short answer is no, but it's the long answer is much more complex. The traditional data that went into the forecast and warning is the coastal tide gauges, and that didn't work well for in case of big tsunami because they just flat-lined here. They're just destroyed. They're plainly destroyed. So because of the coastline is hit the worst with tsunamis. So the data. Some data exists, but only far away from the source. It takes time, and it's much smaller amplitude. So it's more difficult to use because of the signal-to-noise ratio. Engineering design, the engineering fortification. Japan has invested quite a bit into the mitigation by just engineering means. In fact, right now, the most of the coastline of Japan is just surrounded by walls, which are specifically built for tsunami protection. Didn't work in this case because they were under-designed again, and the design is definitely a modeling effort also. That's you have to estimate, how high and how bad the potential impact is going to be, and it was underestimated. This is a very sophisticated tsunami wall that's supposed to automatically goes down because it floods the river. It protects the river, so it goes down only when tsunami warning issues, and it's completely destroyed. It cost probably $500 million just this piece. So very expensive ways of doing the mitigation, and it doesn't always work, obviously. But in terms of the forecast and warning, that's the main problem that Japan has faced. What you see here is the dark blue is the area that was officially designed as evacuation areas for the tsunami. So it's supposed to be worst case scenario modeling assessment of what can happen in case of the tsunami flooding. And the pink is what actually happened. So that's where the forecast really needs to be very accurate, because people evacuated here only to be killed by tsunami, and there was a lot of evacuation areas, and it's repeated in many different places. So that's the real goal of the forecast. So this should be flipped around. The forecast should definitely be conservative. It can never happen this way. And to do that is again, it's difficult because the forecast speed, you want to make it in time. This is a picture that I like from the Indian Ocean tsunami, from Thailand, and that's about 1 hour after the event. So there was no warning in the Indian Ocean whatsoever. There was no tsunami warning capability there. So it was the earthquake happened almost hour and a half before that picture, but no warning, nobody felt the tsunami. There was a lot of tourists, and there's definitely, that's actually the warning came to them as the visual realization of the big tsunami coming in very late. They actually were saved. All of these guys I saw, they actually escaped the wave. There was an interview showing all of them, but definitely, forecast speed is important. You want to do it as soon as possible so that people can evacuate, and people can evacuate. Actually, that's a doable task, because you only have to evacuate immediate coastline. So it's if people know what to do, when to do, and how to do that, that's possible. But it has to be done fast, and accuracy, of course, as it show, it's also has to be. If it's an accurate forecast, it's not only useless, it can be dangerous, it can be killer. These two don't work well together. You can do it fast, but it's probably not going to be very accurate, and you can do it very accurate, but it's going to be very late, most probably. So you have to come up with a compromise solution. That's still a problem that we're still facing, and just showing you what has been done so far. And again, that's the forecast sequence. You assess it with the actually tsunami measurement data. That's important to get the accuracy down. So that's what we found. If you constrain your models by actual tsunami measurement data, the accuracy goes by the order of magnitude higher. So you have much better accuracy. Still may not be enough everywhere, but that's why you have to actually measure tsunami, then you can get a good forecast. You can do the assessment of the source, and then do propagation, and then the actual forecast is that. The impact of the coastline, what it shows is, this picture is the Kahului, Hawaii. For the Japan tsunami, that's the forecast. Actually, it's the first sort of flooding forecast that has ever been done, showing the flooding of Kahului, and Kahului was, the whole Hawaii was evacuated, but there was, in some sense, an easy task, because it's about 6 to 7 hours before the wave hit after the earthquake, and all the capability was already implemented at that time. So if it didn't work, in this case, we should probably have thrown everything away and went to jail for spending the money, taxpayers' money. But it worked well for the far field, so again the models. That shows the animation, how this modeling, it's just animation of the models. The model actually runs much faster than even that animation, because we optimize the model to run as fast as possible. But it zooms into this Hawaii chain, then it's like every single hour, and then it's island. And then the harbor level, about 10 meter to 30 meter grid resolution, very high resolution, up to building size resolution. That gets you the estimate of flooding fairly well. That's what we see, at least. So that's then you can compare it. You know, after the fact, you can compare, and that's important to make sure that you actually you're getting some forecast skills. Because if you don't have the metric that to compare your forecast results with observations, then you don't know how well you're doing. You don't know how well you're improving and what to improve. So the tide gauges provide important independent data. The problem with that is we still don't know what's the good metric. How to estimate how good we've done. So visually, it's the comparison often appears well, but in some cases it can be underestimated, but then can be very small waves. So where the noise to signal ratio is very bad. Is it a bad comparison? Is it a bad forecast? Or is that the metric that we designed? Right now we're using a very simplified one, just compare the maximum computed wave with the maximum measured wave, and it showed that they may not be the good metric to use, because the big waves and small waves, they have the same weight. And we're not sure if that should be the case, because the forecast skills, it almost favors the small amplitude tsunamis, which are almost impossible to get right. So you don't really know how well your forecast does. And so that has been done computed for not just for Hawaii, but it was almost 50 like most populated coastline communities around the United States. That's what we've done this high resolution modeling for, and all and the comparison with the gauges darts all over the Pacific. That shows the deep ocean comparison. The red is the model, the blue is the measurement. Again, this tsunami was fairly well instrumented, and for the far field we've done fairly well. So that shows it's small graphics. It's done for the purpose, so you don't see how well we've done. But I put the numbers here. It's especially for larger waves, the accuracy, which is again the very simplified metric of just ratio between measured and simulated, is about it's about 80%. For the smaller ones, about 70%. So 70%, we still have 30% error. Is it a big error or small error? I don't know. What that seemed to indicate that if it's a flooding event, which is actually the trigger for the evacuation. So that's what we're trying at least to get right. So the flooding is forecasted very robustly with this error. So if it's a big flooding event, it's going to be triggered. Well, it's going to show that, and it's going to show the flooding forecast pretty well. So that was done for this event, but we actually have done it for many other events too. So we're starting to get the forecast skills, and these numbers that I showed, it sort of hold for other events. Most of them are smaller. But the last sort of big one was in Chile here at 2015. Well, the very last tsunami was actually in January, the end of January in Alaska. It was a small tsunami, but it was a big scare because the earthquake was fairly large, but it was very unusual. It was not on the typical sort of what we call subduction zone. It was not a typical thrust event that creates big tsunamis. It was in the intraplate, inside the plate. So it was big earthquake, but not very big tsunamis, but it was detected all over the Pacific. It was kind of interesting event. Data is good. Tsunami, we like these tsunamis that don't create damage but provide a lot of data. So that's because it gives us opportunity to look at the models and to see to improve our forecast skills. That's what we call it. It's the term from the Weather Service actually. And it was in Chile. We don't have high resolution models for Chile for the real time, although we're working with Chilean government to produce some of those. But for the models in US, that we've done pretty well, and it was based on the two darts and we've done some statistics on on the model that still holds. So we about, an average, about still 30% error, but for large amplitudes, we actually do better. So which is great, because that's what we want. So if we have large tsunami propagating, our forecast is actually doing pretty well. Now, and that's some pictures from the ground zero. I'll just zoom through here. The biggest problem, the challenge that we now face is the challenge of what we call near field forecast, because that's where the timing and the amplitudes are severe. Both. It's a very short time, and it's again Japan Tsunami. They have a lot of actually instruments. Many of them were not real time, but we got a lot of data, and we could use that to do fairly high. It's after the fact we've done in collaboration with Japan colleagues, and we've done the problem. One of the issues that we face there, since our main goal is to actually the colors are the forecasted flooding. This is the coastline, and that's what was flooded, and the white line is the measured inundation extent. So we've done pretty well. I mean, it looks like we can compute, and that was actually the forecast based on these real-time observations. So the actual computations were done after the fact, but it was done as if it was done in real time. But how good is it numerically? It's well, sort of quantitatively, we still don't know. One metric for the flooding, for the actual flooding, we thought of just the area of flooding, and that turned out to be about the same error, about 70% error. If you compare the flooded area of forecast and the measurements. But that's a difficult metric to get, because you have to. I mean, this was a huge survey campaign to get all these coastlines. It's very difficult. I know, I've been to the surveys. You have to walk the line. It's a huge amount of surveying that needs to be done. So that's another thing. Since this is the actual goal of the forecast, to produce the flooding extent, and how accurate we can do that, we don't know. So that's. And the relevance of the local problem, of course, is the Cascadia subduction zone. So this is, we have this comparison of this Japan tsunami. It's 2011, and that's one of the projections of the future 9.1 Cascadia subduction zone event, which is going to be larger if the whole subduction zone ruptures, which is some of the scenarios, most of the scenarios shows that, not most. Now there are there are papers showing that it actually can be only part of the subduction zone can rupture also. So we don't know that, but the whole rupture is also feasible. And this is comparison of the sort of maximum amplitude that you can expect. The red is actually measured, sort of run-up fights along the Japan coastline, and the model, the gray dots are the models along the coastline of Washington, Oregon, and Northern California. These are higher because of the geometry, pretty much, and the exposure is actually fairly similar. But remember, Japan is the most educated population in terms of the tsunami threat and tsunami exercises. So, it was actually less than, it was about 16,000. It was the initial estimate, so about 20,000. I think it's just over 16,000 that was killed. What's going to happen here, we don't know. There's a lot of efforts going on the ground level also. There are the educations, the campaigns, the evacuation drills going on, but how well the population is prepared, we don't know. And a lot of population is actually transient, because there's a lot of tourists there, and that's a different, different paradigm. You can teach the local population what to do, but the tourists is a different matter. So that's definitely.
How well are the inlets and the rivers modeled?
Yeah, well, this is the course model, but yeah, well, let me show this. We can zoom into so this is the Long Beach Peninsula, which is a big problem in Washington, in the state of Washington. This is Columbia River. And the problem is that it's pretty much overwashed by the tsunami, which means that there is no way to evacuate people there. And that's a very popular tourist destination, actually, in Washington. So that's, and we can model that, you know, but it's when we work, there is a lot of this what's called National Tsunami Hazard Mitigation Program. It's a group of interagency, intergovernmental group that gets together and decide what to do with the warnings, for example, like that, or with the threat assessments like that. And there's a lot of discussions of how to deal with the Long Beach problem, and we, you know, the first step is to assess the hazard, and we do the simulations and give it to emergency managers, and they just say, what do you want us to do with this? For example, there was happened actually in Seattle. There's a Seattle. I'm from Seattle, so I'm based in Seattle. So we worked with the city of Seattle to assess the hazard. There's this what's called Seattle Fault that goes right through downtown Seattle and actually crosses the Elliott Bay. I don't have these pictures here. And it's known to produce a tsunami about 900 years ago. And this is it. We know that it happened because there was a very good evidence of the displacement there. We know that it was happened once. We don't know if it's going to happen again or if it ever happened before. But we did this worst case scenario as we designed, and that shows fairly devastating impact on the coastline of Seattle, you know, Seattle coastline. And we showed it to Seattle emergency managers. They said, okay, thank you very much for your work, and put it somewhere in the shelf because there's not, I mean, the travel time there was 2 minutes. So 2 minutes, in 2 minutes, the 10-meter waves hitting the very touristy Seattle coastline. You don't know how to manage this kind of threat very much. There's an issue there. You know, we can do this, the hazard assessment, but then how to mitigate this hazard is a different problem. So anyway, just briefly, maybe probably hitting the end of my talk, just to show you what's the state of the art right now and what are the challenges in terms of producing the forecast. I'll just put it in this forecast in the sort of the timeline cycle here, and it's a cycle because the cycle goes around with more data that comes in. So again, this is the forecast. That's what we want to do. The rest are just steps to get to that, to the impact of the potential tsunami flooding, because that's the bulk of the tsunami impact at any community. It all starts with the earthquakes. Well, we talk about the earthquakes only now because again, 70% of the problem. It takes about 3 to 15 minutes to just assess, to just know that the earthquake happened and how big this earthquake is. And 3 minutes is pushing it. 3 minutes. That's when Japan first estimates came out, and that was hugely underestimated. So that may be a problem. So we know that initial estimate is going to be very problematic, very uncertain. But you can still use that because that's the data that you have, and you can run you can do the inversion. Well, in this case, it's going to be very simple. Just scale up our sources with the magnitude of the earthquake, and actually run the coastline. The high resolution models. It takes some time, and even before you get the actual measurement of tsunami, because it's the key to get the actual forecast, and you already over 30 minutes timeline, and you do some forecast. You can do some forecast, but it's probably going to be garbage in 50% of the time. Very inaccurate, not garbage. No, I don't want to say it's garbage, but it's going to be very inaccurate. And then you repeat this cycle, but that takes more time. You can get this forecast more and more accurate. It would be great if we know where the earthquake is going to happen. We're still waiting for the seismic community to give us this promise that they can predict earthquakes. At least the location, some ballpark magnitude, whatever. That would be great. Then we can still use the same cycle of the forecast and provide the forecast beforehand. and be ready to, for all the and then for the updates. That's probably unrealistic future. From what I hear from our seismic colleagues, we shouldn't expect any earthquake, short-term earthquake prediction anytime soon. So we're still stuck with this 3 to 15 minutes, and that's the 15 minutes is just big earthquakes. The shaking continues, the rupture continues for almost 10 minutes. For example, the Indian Ocean tsunami was rupturing for about 10 minutes, 1,000 kilometers long fault. So it's until it's complete, the rupture is complete, you can't really get assessment of the source. But so we're stuck with that initial assessment there. We can do the modeling now very fast. The talks that I heard yesterday were great. It's the the computer, the Morse law is sort of slowing down, but it's still working great. We still have we're just waiting 10 years doing nothing with our modeling. We got 2 orders of magnitude faster models. Fantastic. The GPU is just magic. Just 100 times faster models. So now we optimized our models already to run in like 10 minutes. Now we can do it in seconds. So it's to do the computations. We can always use all the computer capacity we get. It's of course, but we can optimize it to get very fast modeling. And if you have the data in 10 minutes, then you can get the forecast less than 15 minutes. The key, of course, so the computation is, at least right now, doesn't seem to be the bottleneck of this process. Is the measurements, because the key is the tsunami measurement, and the problem with this is, you can put that's coming back to your question. You can put detectors very close to potential sources. We actually know where the potential sources are. They're around these, big subduction zones, big faults there. The problem there is that when the earthquake happens, it creates huge shaking, and that the tsunami, if you could, that's an example of actually, some of the cable system that were installed in Japan. You see this black light. It's a noise. It's a seismic noise that's recorded on the gauges, in the deep ocean gauges, and you can see tsunami. There's tsunami embedded into that. So there's additional problem that there's this noise. For us it's noise. For seismic community, it's data. So it's classical. Somebody's noise is somebody else's PhD. So that's exactly what it is. But this creates the problem for us, the tsunami forecast capabilities. But it's solvable problem. But you can filter that out because the frequency is much higher. But to filter it efficiently, you have to have very high frequency data stream, and that's another problem. The buoys are, the independent, they're self-contained systems. They run on batteries. And if you have very high frequency of the data stream, then the batteries just run flat pretty soon. So a lot of engineering problems, but the engineers are solving those. So you can actually put this next generation buoy that now is being deployed that has very high frequency, can send data real time, and you can put them very close to the source. But then to resolve this source, you have to have much more of them. So this is the existing DAR buoys. And this is, so there's one of the proposals that went in. So it's order of magnitude more data. And these buoys are not, they're not cheap. They're, but the biggest cost is actually the ship time to deploy them, because the buoys themselves is probably 300,000. A pop, but then to deploy them, it gets them almost up to $1 million per system. However, the alternatives, there are some alternatives. The cable system was big in Japan after the it was before Japan tsunami, but after the event, there was huge efforts to deploy this massive cable system with the same detection, the same detection that we use in our,
How long does one of these buoys last?
Good question. They actually designed to last. So the batteries can last for 4 years. So they optimized, and the reason is that actual detector is sitting at the bottom, and the bottom is very stable environment. It's very cold, continuous, temperature, very good for batteries, so they can last forever. The problem is the buoy, the surface unit, that has a lot of the marine environment is very tough environment. It's arguably it's tougher than space actually, because it's the salt corrodes the material, the waves. It's just you can't use, for example, the solar panels because they become opaque in a couple of days by salt. Salt just put on top of that, and it becomes useless. So right now, since it's operational system, they want to make sure that they work, so they actually change it every year. So there's a ship that goes around and change them every year. But the idea is to have sort of disposable system that you just put out there for maybe 2 years, because the surface buoys is still challenging, or maybe 4, and that makes it cheaper. But because the ship time is huge part of the cost. Well, there's no ship time here, but the cost of this system, this massive system, I think it's pushing $1 billion. It's a hugely expensive system, and they have a lot of. I mean, they started to deploy it, shortly after the 2011, and there's a lot of issues. It's great data, it's cable. They don't have problem with power, with time frequency, but noise is a huge problem. Because we know that in oceanography, the shallower you get, the more active the environment becomes. So that's why they put this additional, string that goes beyond the shelf, and it's just a recent addition, and they still have problems with that. So, but it's coming up online. In Japan, the decision is made that they're going to deliver. And that's fantastic data. We haven't seen the data yet. We have seen some pieces of that data, but not real-time data. And with real-time, there's going to be a lot of issues there. There's similar efforts in Canada and in the US, and there's, the actual problem actually in Japan is here. It's an unkind trench, because that's where they have been expecting tsunami all along. It just happened in the wrong place, because all the population is here. Tokyo Bay is here, Yokohama, all the exposure is there, and that hasn't happened yet. They've been waiting for it for 50 years. It happened here, but it hasn't materialized here. So, but the system went into this place. There are some components in the other locations too. There's some other data. The GPS turned out to be a very good source of data since the tsunami is generated by the displacement that earthquake generates. Seismic data is very bad data. It's very difficult data to get this actual permanent displacement out. The GPS actually measures permanent displacement, so it's a better data than seismic. The problem with that is that they're all on land, so it's one-sided. It's skewed data set, difficult to invert to get the actual displacement that's offline. And the other sources I just mentioned, briefly, the meteor tsunami is actually, for the East Coast, is a bigger problem than the seismic tsunamis, because in the Atlantic, the earthquakes do happen, but not very often. And there was the event in 2013 that created, somebody was washed out from the pier, so there was a lot of media coverage. There was a system, the weather system, that's a weather system propagating across from land to the ocean. And we model that, just assuming there's not a lot of data there, we just assume that that's proxy for the pressure field that can create disturbance on the ocean. And that's the disturbance, actually, there's an interesting phenomenon called Prudman resonance. So if this system propagates with a certain speed, it can actually resonate with its resonance speed for generated tsunamis, and that's actually, it fit the data pretty well. So that's just this crude model. We were able, because this was detected on our observation system. There's a dart sitting there. and on some coastline. It actually fit fairly well. We do better with our seismic data, but it was very encouraging that this potentially the capability that we can use to use this capability, the data is going to be the key, because that was it was really a shot in the dark. We say, okay, we'll just use that as a proxy for the pressure field, and there is no high-resolution pressure field available for the meteor community. The asteroids, we actually have done since. It's actually very similar to this meteor tsunami field, because we decided that the actual unknown in terms of the asteroids is how big of the tsunami can asteroid like this, the one that you showed in Chelyabinsk, with a pressure wave can generate. Can pressure wave that's propagating with the speed, speed of sound, create any tsunami? The thing is that, the speed of sound, 330 meters per second, it's about the same as the propagation of tsunami in the deepest part of the ocean. So the tsunami actually almost hitting the sound barrier if it propagates like in Mariana Trench or something. So it's close in terms of this resonant speed. So we've done, and the reason why this is important is that the big impact like KT or maybe even Tunguska will obviously create a big splash, big tsunami, and maybe even the end of civilization event. But if you try to assess the risk, and that's the work joint with NASA, it's Near Earth Object Group. There's the one that's actually here in where's that?
Are they down?
Ames, and the Ames, the Ames. The way they, it's coming back to this, to the risk versus budget versus what do we want to do with this problem, is that they assess the risk as in terms of fatalities per year, and if you put this plot, diameter of the impact of the asteroid versus fatalities, the big ones. There is a bump there, but there's uncertainty in the middle, and the uncertainty is related to the ocean impact. 2/3 of the meteorites will go into the ocean just because 2/3 of the Earth is covered with water, and the impact of that, or the effects of this impact is very uncertain, because the modeling is very difficult. Actually, it's extremely difficult. The hydro models that show, this is what is it, few microseconds well, maybe a few seconds, 10 seconds, 100 seconds. My God! So that's stretching it to the limits of the computers. It's but to propagate these waves and to see what the impact is pretty much impossible with the hydro models. So we worked with them to get this input and to see, this and actually impact from the shock waves, and to see what it can create. And we've done some exercises. There was a workshop in Seattle that showed that this model, I think it's similar to Tunguska asteroid, to put it somewhere in offshore Washington. Why not? Because there was where the workshop is, and to assess the impact. And since that was a fairly small event, and the assumption is it's completely disintegrated, it's just a shock waves that hitting the ocean, no actual impact. It's not an end of civilization event, but there is some substantial tsunami that creates this event creates, and it depends very much on where exactly this impact is. If you hit the deep ocean, say Mariana Trench, then the triggering is almost perfect actually. So it's an interesting, it's unfinished work. We ran out of budget there, but this was very exciting things to do. So I'll stop here. Thanks for the.
Run just a little over. Any other quick questions?